morning, students. Today I am going to discuss about the ideal gas. What are all the assumptions involved in ideal gas, and what about the thermodynamic properties of an ideal gas? Here we have two assumptions. One is volume and another one is intermolecular forces of attraction. First, let us consider it is a container. It is filled with a certain amount of gas. Okay, it is filled with a certain amount of gas. This is the container. This is the total volume of an ideal gas. This is volume of an individual molecule. Volume of an individual molecule. From the figure, I may be understand the total volume occupied by the gas is much greater than that of volume of an individual gaseous molecule. So total volume is much greater than that of individual volume. This information leads to first assumption, that is volume of the individual molecules is assumed to be negligible. First assumption. Second information, listen, what is the distance between the molecules? This is distance between the molecules. And what about the size of the molecule? This is size of an individual molecule. This is distance between the molecules. This is size of an individual molecule. From the diagram, I maybe understand the distance between the molecules is much greater than that of size of an individual molecule. Distance, second assumption, second information, the distance between the gaseous molecules is much greater than that of size of an individual molecules. Hence, the intermolecular forces of attraction between the molecules of the gas. Intermolecular forces of attraction between the molecules of gases. Intermolecular forces of attraction or intermolecular forces of repulsion is assumed to be negligible for an ideal gas. Second point, intermolecular forces are assumed to be negligible. First assumption is volume of an individual gaseous molecules is assumed to be negligible. Intermolecular forces of attraction and repulsion is assumed to be negligible. These are all the two informations for ideal gas. Next, formulation of ideal gas law. First point from based on Boyle's law. Boyle's law states that the molar volume of an ideal gas is inversely proportional to the pressure of the system or pressure of the gas. Molar volume of an ideal gas is inversely proportional to the pressure of the gas, subject to the condition temperature is held constant. When temperature is constant, the molar volume of the ideal gas varies inversely with respect to pressure. From this information, I can write like this: the product of pressure into volume, the product of pressure and volume will be constant. Clear? This is a statement from Boyle's law. Second information from Charles' law. Charles' law. Charles' law states that molar volume of an ideal gas varies linearly or varies directly proportional to the temperature. Volume as direct proportional to temperature, subject to the condition pressure is held constant. Pressure is held constant. When pressure of the system is constant, volume will vary directly with the temperature. From this information, I can write like this: the ratio of volume to temperature is constant. The ratio of volume to temperature is constant at constant pressure. Third information from Avogadro's law. Avogadro's law. Avogadro's law says that the molar volume of an ideal gas, is directly proportional to number of moles of the gas. Subject to the condition at moderate or at the moderate temperature and pressure, or absolute temperature and pressure. Normal temperature pressure means temperature is 0 degrees Celsius and pressure is 1 atmosphere. At normal temperature pressure, the molar volume of an ideal gas is directly proportional to number of moles present in the gas. From this equation, I can write the ratio of volume to number of moles is equal to constant. Subject to the condition at normal temperature and pressure. Combining these three laws, Boyle's law, Charles' law, and Avogadro's law, I may achieve PV divided by N into T is equal to constant. PV by N into T is constant. This constant is replaced by the notation R. R is nothing but universal gas constant. So this equation becomes PV is equal to nRT. This is the ideal gas law equation or equation of state for ideal gas. Ideal gas law equation or equation of state for an ideal gas. Equation of state means an equation which connects the pressure, volume, temperature of the system. P stands for absolute pressure, V stands for molar volume, N stands for number of moles, R stands for universal gas constant, T stands for absolute temperature. Clear? This is the equation of state for an ideal gas. One more important information: the volume of an ideal gas V is equal to nRT divided by P. N is equal to 1 gram mole or mole. 1 mole or gram mole, both are same. R is equal to 8.314 joules per mole degree Kelvin. Temperature is 0 degree Celsius, that means 273.15 degree Kelvin. Again pressure, 1 atmospheric pressure, R I can write like this: 1.01325 into 10 to the power of 5 Newton per meter square. So gram mole gets cancelled, Kelvin gets cancelled. This joules is Newton gets cancelled. Remaining thing is meter cube. The answer is 0.022413 meter cube. Meter can be done into liter. 1 meter cube is equal to 1000 liter. Okay, 1000 liter. Meter gets cancelled. The answer is 22.413 liter. This means that at normal temperature pressure condition, 1 mole of an ideal gas, at normal temperature pressure condition, 1 mole of an ideal gas occupies 22.413 liter of volume. This is the standard condition. This is for 1 gram mole or 1 mole. For 1 kg mole, this occupies 22.413 meter cube. Clear? A gas, one which obeys this law, that gas is called as ideal gas. Okay. Next, thermodynamic properties. Thermodynamic properties of an ideal gas. Okay. First point. Internal energy. Internal energy. See, already I said that product of pressure and volume is constant. Product of pressure and volume is constant, subject to the condition temperature is held constant. Internal energy depends only on temperature. Internal energy depends only on temperature. It does not depends on pressure and volume. It does not depends on pressure and volume. So I can write like this: changes in internal energy upon changes in pressure or constant temperature is equal to 0. Similarly, changes in internal energy with respect to pressure at constant temperature is equal to 0. Clear? Internal energy of an ideal gas changes only with respect to temperature. It is independent of pressure and volume. Next point, enthalpy. Internal energy, next enthalpy. Similar to internal energy, enthalpy is function of temperature alone. It is independent of pressure and volume. Next point, Joule-Thomson coefficient. Mu. Notation is mu. The unit for Joule-Thomson notation for Joule-Thomson coefficient is mu. Joule-Thomson coefficient for an ideal gas, that means changes in temperature upon changes in pressure with respect at constant enthalpy is equal to 0. Joule-Thomson coefficient or Joule-Thomson effect, this information is very much important in throttling process. That means when a gas is compressed to high pressure, if it is allowed to pass in a flow restricted device, there will be a pressure drop. Decrease in pressure causes to increase the temperature. Decrease in pressure causes to increase the pressure or decrease the pressure. Its magnitude and sign will differ with respect to pressure. Because ideal gas neither warm up nor cool down during the throttling process. This Joule-Thomson effect is the main reason in our home appliances of AC unit. Clear? It will be discussed later. The point is Joule-Thomson coefficient for an ideal gas is 0. Joule-Thomson coefficient is nothing but variation of temperature with respect to pressure at constant enthalpy. Clear? These are all the important information for ideal gas and ideal gas law. Clear? Main thing is volume inversely proportional to pressure. Volume directly proportional to temperature. Volume directly proportional to number of moles. These are all the important information. Two assumptions. In ideal gas, volume of an individual gas is assumed to be negligible. Volume of an individual gaseous molecule is assumed to be negligible. The intermolecular forces of attraction is assumed to be negligible in an ideal gas. Okay, this is the information regarding ideal gas and ideal gas law. Thank you.